The next example that we're going to look at is actually trying to replicate an example that's in Shumway and Stouffer's book. This example deals with things called varves. Varves are sedimentary deposits from melting glaciers over the spring and summer seasons. And the data used here is a measurement of the thickness of that deposit put by that glacier at one location in Massachusetts. We have information from 634 years of deposit measurements that start about 11,800 years ago. So there wasn't somebody who was 11,800 years ago who actually got out a piece of paper and a pencil and started recording these measurements. Rather, one can see, since these are sedimentary deposits, one can see the yearly deposits that were left by the glaciers. Okay, so this data, since this comes from Shumway and Stouffer's book, this data is actually in their ASTSA package from R, and the data is in a a vector called varve. I'm going to just simply rename that as Y. And let's go ahead and plot then the corresponding data. And so this is what we have. We have basically year of deposit. We have, that should be Y there, not X. And what we can see here over time is that, we have a little bit of trend going on here. Also, we see that we have some extra variability in certain segments of the corresponding data. And so for that reason, Shumway and Stouffer said, hey, let's go ahead and work with the log transformation. So let's go ahead and do that ourselves. So I'm going to let X now be equal to the natural log of Y, and I plot my data like I would normally. And this is what we get. And we see now that we have, in terms of stationarity with respect to the variance, this looks a lot better than what we had before. Okay, so with this data now, this log transform data, let's go ahead and do an ACF and PACF plot for it. And this is what we get here. Notice that we have this long memory in terms of we have these autocorrelations. This is out to lag 50. We have these moderate in size autocorrelations that seem to persist for a long period of time. This is a characteristic of long memory data that needs an ARFIMA model. So to actually estimate now a model, to estimate a model, we're not going to worry about right now any AR or MA component. So to estimate the model, we need to find the mean of the series. We need to adjust the series by the mean, and then we're going to use the frac-diff function once again. Here's my adjusted data. I then look at the corresponding results that I saved in mod.fit. And so this is what we get. Here is D hat. So it's about 3.7. Notice the z-test statistic. It's very large because I have a very small standard error, and so of course then my p-value is quite small. Okay, so some notes. Here's what the actual estimated ARFIMA model would actually be, how it would be actually stated in this case. 1 minus b raised to the 0.37 power times xt minus that estimated mean 3.1179 is equal to wt. Now, for how Shumway and Stouffer actually approach this in the book, is that they use an M of 30, meaning, and I briefly explained this before, basically a truncated likelihood is actually being used to estimate the data. When they actually estimated the model for the book, they use M equal 30 rather than the default of M equal 100. They don't really say why. And so since I'm trying to duplicate the results that are in the book, now I'm going to re-estimate the model with only M equal 30, In the end, there's very little difference. D ends up being 0.384. I suppose I could put a D hat on that if I wanted to. Okay. So what I decided to do next was to investigate some of the aspects, the underlying aspects of these models. And so I thought, okay, why don't we actually, let's say, come up with the pi's ourselves? So remember, this 1 minus b raised to the dth power can be written as a Taylor series expansion, where these coefficients on the Taylor series expansion are these pi's. So let's actually just find them ourselves. So what I did here, I created a vector called pi.vect, and I'm going to put all the pi's in. The way I create a vector is I use the numeric function r, and I want it to be as long, this vector, as my data. So length of x.adj. Now, pi sub 1 I know is going to be negative d, based upon what we've seen previously. And then simply I'm going to use a for loop where I'm going to find pi sub 2, pi sub 3, all the way up to the last pi. How do I do that? I use this recursive relationship. I program that in there, and this is what I get. Notice here is pi 1, here's pi 2, and so on. Of course, pi 0 is equal to 1. So this is the relationship I use. Now note I also work with some stuff trying to find the w's, the residuals. We'll talk about that a little bit later as well. Now one thing that's important to point out here is that if you take a look at the corresponding example that's in Shumway and Stouffer's book, they also try to find the pi's. In fact, they do a plot of them. But I don't think their plot is correct, because their pi 1 ends up being 0.3079. But we know that pi 1 should be negative d. So I don't think that their values are correct. I think maybe they maybe accidentally did it wrong in their plot. Other things that I do matches up, but not this. Okay. So let's talk about residuals then. Now, the residuals can be found using the residuals function in R. So that makes it really simple. Again, when I've taught this course in the past, I didn't have a way to do that, and I actually did find the residuals by hand, or by hand by programming in the code, and that code is actually what's in above in my corresponding code that I presented on the previous page. Anyway, so to find the residuals, I can find residuals mod.fit. Here are the first 6. Using the tail function, I find the last 6 as well. So while this residuals function is convenient, I think it's at least good for us to at least see the process of how one would find these w's ourselves. So remember, w sub t is equal to the sum from j equals 0 to infinity of pi sub t times x sub t minus j. So here's how I've written out my corresponding wt when I write out the sum. So then to find the corresponding residuals, let's plug in t equal 1. So w1 is equal to xt. At t equal 2, w2 is equal to x2 plus pi 1 times x1. And you can keep on going all the way to the last data point. We have 634 observations, so we have w sub 634. And so if I come back up here, this is essentially what this code does. You can look through it on your own, but real briefly, I create a vector called w where I'm going to save all my results in. I find the very first w, w1, which is equal to x1, or in this case it's the mean adjusted x1. And then through my for loop then, I'm able to find then my other w's, where I take the current w that I'm at. So if let's say I'm at w2, of course that would have x2 there. So just to show you, let me come back. w2, x2. If I was at j equal 3, I would be at w3, I would have x3. And then what I need to do is find the linear combination of the pi's with the x's. So notice how the subscripts are essentially going in the opposite direction here for the pi's and the x's. So the way that I handle that then is when I want to take now the sum of the pi's times the x's, I have my pi's here in a vector, and I take it times the reverse of my x's that are in my x data vector. So that's how I was able to match up the indices nicely. So when I go through that and run the for loop, this is what I get here. I create a data frame called all. Here's my x's, here's my w's, here's my pi's, here's the first 6, here's the last 6, and notice, for example, my, let's see now, my second residual, 0.135, notice how that matches up with what the residual function has. So again, this helps me verify that indeed I understand what Shumway and Stouffer is doing. I understand what R is doing in this problem or with this data. Okay, so now let's do some plots of the ACF and PACF. So similar to when we had an ARFIMA model, we would estimate it, and then we do some various diagnostics involving the residuals. So what I'm going to do here is do residual ACF and PACF, and the reason being is because I want to see if changes need to be made in the model. If there are significant autocorrelations or partial autocorrelations, those significant values at particular lags lead me to choose a way to proceed in terms of if I need to add AR components or MA components to the model. So I do a plot of my estimated ACF and PACF, and look at this. First of all, again, ignore lag 0 ACF. All the autocorrelations, partial autocorrelations, are pretty much within the plus or minus 1.96 divided by the square root of n boundary lines that are on that plot. There are some values that are marginally significant, but then again, look at this. We go out to lag 100, so you would expect some that might be just a little bit outside there. That's not necessarily alarming to have. So from this, it looks like this very simple model seems to be appropriate for the data. So what about now doing some forecasting? So x tilde sub x35, so the first value next in the time series, using information up to 634. How would I find that? Well, I'd find the expected value of x635 given my past information. I can write my model out in terms of this w with the x's and the pi linear combination. This w sub 365, that shouldn't be 365, that should be 635. Sorry about that. That expected value given my pass up to 634, that expected value is 0, and so I'm left with this linear combination of the pi's with the x's. So one could go ahead and find this. Now, with the actual data, since I did mean adjust it, so I'm going to now need to add back then the mean to actually find the corresponding forecasts. Also, if you remember, we actually started with a log transformation of our original data. So because of that, I'm going to need to back transform to the original numerical scale for the data. So let's go ahead and simply use the forecast package to do these forecasts. So I have forecasts. My model fit object is mod.fit. We'll just try 2 points ahead and 95% intervals. So here's then my corresponding point estimate. So this would actually be z tilde sub 635, 634, where my z's correspond to my mean adjusted data. Here's the corresponding forecast. I can now take into account that mean adjustment by simply putting into a data frame here my forecast plus the mean of the series. I do the same thing with my lower bound and my upper bound and my corresponding 95% intervals. And so now here we have x tilde 635 with a superscript 634. Since I used the log transform to begin with, I use the exponential function. So finally then, I get y tilde 635, 634. Now, one thing I should mention with this series, I should have done at the very beginning. Unfortunately, Shumway and Stouffer do not say anything about the numerical scale. So I don't know if this is measured in centimeters, inches, or what it's measured in, which is actually too bad. Now, a big picture thing here would be, well, what would be the purpose of these forecasts here? After all, this was, thousands of years ago, essentially when this data was first coming about. And we are forecasting, something that is for thousands of years ago. So what's really the purpose of doing forecasting here? And I think that's kind of up to debate for this particular problem. I think the best conclusion that I can come up with is that, maybe a model like this would be helpful for understanding current glaciers and understanding the varves that they produce. And so I think that might be reasonable. I am not a hydrologist, so I can't really comment further on why this kind of forecasting would be important. Now, another little interesting note is that Shumway and Stouffer also examined this data set in a different place in their book, and they work with ARFIMA models for this data, where they allow full differencing to occur, and they suggest an ARFIMA 1-1 model would be appropriate. However, in another place in their book, they come back to this data and they apply what's called a unit root test. Without going into all the details behind it, all this is a hypothesis test that looks like this. Is an AR parameter, phi1, is that equal to 1 or not? The reason why that's important is as follows. Let's say that this was equal to 1. Then we have essentially first differences. And so a unit root test correspond to, if we think of roots for this expression here, and that is one tool that some people use to help make a decision about, well, do I need differencing or not? And they do this test, and they conclude from the test using a p-value that no, reject HO, suggesting that a full difference that you have for this particular ARFIMA 1-1-1 model is not actually needed. So therefore, from that, then they said, yes, the ARFIMA approach is better. I guess I prefer to think of it more this way. With the ARFIMA model, we're only estimating one parameter, D, where with the ARFIMA 1-1-1 model, you're estimating 2. And in terms of model parsimony, seems like our ARFIMA might be a better approach for this modeling then. Okay, so that concludes that particular example. I want to end here, or I want to do one more example, I should say. Going back to this ARFIMA model, where we simulated data from an ARFIMA 1.30, where phi1 was 0.2, mu was equal to 0. And let's say that we didn't actually know what model to begin with from the start. How would I approach, let's say, model building in this situation to choose an appropriate model? Excuse me. So what one would do, first, similar to what we started off with, is you find the estimated ACF and check to see if it has the characteristics of a long memory series. Then if it does, then look to estimate D. Then get the residuals from that particular model's fit, and based upon what you see for the residual ACF and the residual PACF, you approach it very much in the same way that we've done with the ARFIMA modeling, where you look at those plots to make decisions of, okay, what should I use for P, what should I use for Q? Then use FracDiff to estimate then these new potential models that will update then the particular values for D as well. Okay, so let's approach this in this same way. So, let's estimate an ARFIMA 0D0 model to the data. So I estimate that particular model. I summarize the model's fit. Here's my D hat. Notice that it is significant. I can get my residuals from using residuals mod.fit. And here's the corresponding ACF and PACF plot from these residuals. And interestingly, what we see here is that there's essentially no significant no significant autocorrelations or partial autocorrelations here, despite us knowing that an AR1 model should be appropriate. So I would have expected maybe to see something like this on the PACF plot and to see a tailing off to 0 here. Again, ignore that autocorrelation at lag 0. So that's kind of interesting. This is suggesting a different model than what is actually the correct model. Now, why could this be occurring? Well, it's probably, this is probably the reason. Notice that the value for phi1, the true value for phi1 in this particular case is, I think it's 0.2. Let me just double check. Yeah. So it is quite small. And since it's so small, perhaps that's why we're having problems seeing that indeed that we have a significant value here for these plots. And so I expect that that's probably the reason why this is occurring. Now, let's say also that I wanted to explore these residuals further from this kind of a model. And I wanted to obtain the residuals, let's say now from a fit of an ARFIMA 1D0 model. So how would I go about doing that? Again, I write my X of t out in terms of then this linear combination with the pi's. So that's what I do here. Then I can now multiply it by the 1. I can also multiply it by the b times phi1. And so now I have a representation for WT. And again, one could go through the process of finding all then the corresponding W's. So let's go ahead and estimate this ARFIMA model once again. That does have that AR component to it. So here's the code that we've seen previously. I estimate then the corresponding model. And let's go ahead and now find the residuals. So with these residuals then, I can do an estimated ACF and PACF plot. And again, we don't look at lag 0 there. And again, it looks like we have something that you would expect from white noise. So it looks very similar to the plot that we had previously when we didn't even estimate the AR parameter. But if we also took a look at this right here, we can see that definitely that AR parameter is significant. So it's kind of interesting. Now, if you actually look at the AIC between the two models, the AIC for the model that includes phi1 is a little bit lower. So according to that criteria, in addition to the significance test, perhaps then the model with the AR component is a little bit better to use. Okay, so some final notes here. If a good estimate of D can be found, I suppose what one could do is transform your time series that you're working with to 1 minus b raised to the d power times x of t. Use that as essentially your observed data, and then approach ARMA modeling like what we did before, where you could use the ARFIMA function, the ts.diag function. I suppose that one could do that. I have not done that myself. I have not seen others do that, but it seems like this would be a reasonable approach to follow. Now, as I mentioned earlier, there's actually a couple other packages out there that can estimate these ARFIMA models. Just to give you an idea of how these particular packages look or work, let's look at the ARFIMA package itself. And they have a function called ARFIMA, where you put in your data and you put in the corresponding order for your model. Note that on D is going to be estimated here, even though I put a 0 there. So order equal, there's the AR component. And I put that in results called summary mod.fit2. I'm sorry, and this is with my original ARFIMA 1.30 model data. I can summarize the results. This is what I get. So similar to what we've seen before, here's phi hat 1, here's d hat as well. We get z-test statistics, we get standard errors, we also get p-values associated with it. We get a lot of stuff that we've seen before, and essentially this is the same as what we saw before as well. The largest difference is that the estimate of mu is actually done within the function. Otherwise, it's very similar. To do forecasting with this particular package, we can use now its version of predict. The predict function is a generic function in R, and they have a corresponding method function for it. So we can put for the object the results from the model fit. Let's say I want to go 2 time points ahead, and I want 95% confidence intervals. Here's then the corresponding forecasts as given there. You could use that information to find then confidence intervals as well. Very oddly, with this particular object that's returned, let's call it save.pred2. If I do names with it, notice the first component of the list that's returned is actually something that has no name at all. And in fact, if you wanted to try to extract it to see what it is, you can't. Instead, you can use a different R syntax to extract parts of a list. So every part of a list has a corresponding number to it in terms of the order that it is inside the list. So if I use double square brackets with this, I can pull out the first element of that list, and that element then is the corresponding forecast that one will get from that. And what's disappointing is that given how important forecasting is in time series, to have this very odd way to have to try to extract then the corresponding forecast, I find that essentially unacceptable. One can then find the corresponding intervals as well, and here's where we get that. Similar to the fractive package, there is a method function corresponding to plot that will allow you to plot then the forecasts, and this is what one would get as well. So why didn't we focus on this alternative package? Well, you know, the fractive package is much more established. It's been around for a long time, and so that makes me feel as though it's a little bit more trustworthy. I'm not familiar with the ARFIMA package authors in terms of their names. So again, I am with Fractive's authors, so I feel as though that's a little bit more trustworthy as well. And this gives you just a sense of, you know, in R there are so many different packages to use. Many of them do exactly the same thing, or they're meant to do exactly the same thing, and you have to make a decision about which ones to use. And the process that one uses is typically you look at the age of the package. Has it been updated recently? You look at the author names, and if you're familiar with the area, you should recognize some of the author names in terms of if you can trust that package. You know, and so those are the kinds of things that one uses to make a decision about which package to use when there's more than one choice. In the end, though, all packages that do some kind of ARFIMA modeling in R could definitely use some improvement. The fractive package is definitely not perfect. So then that concludes in this introduction to ARFIMA models.